Hello and welcome to Europractice's webinar series on silicon photonics. I'm Ramsey Selim from Tyndall National Institute, the Europractice Service Center for LioniX International. This webinar will be dedicated to LioniX technologies, where Robert Grootjans will give you an overview of their famous Triplex platforms. But before we begin, let's find out how you can access the technologies through Europractice. You can visit our website where you can find out the full LioniX technologies offered through Europractice, such as their Triplex 850, 1550, and the visible platforms. After you have chosen the technology you want to work with, you can contact me, Ramsey Selim at Tyndall. On our website, you can also find out the LioniX MPW schedule runs. On this slide, you can see the run schedule for 2020, which is regularly updated. The dates in the schedule are the final deadlines for submitting your GDS file. So we highly recommend you submit your draft layout to us at least 2 weeks before the deadline. This means we can give you our feedback on any adjustments you may need to do. For any further questions or information on the LioniX technologies offered through Europractice, feel free to contact me on europractice.gateway@tyndall.ie. And here with us is Robert from LioniX. Over to you, Robert.
40 minutes about what LioniX has to offer in our multiple MPW runs, different platforms, but also in general, what kind of technology we are doing. Let's see if I can go to the next slide. Yeah. So this is a little bit of the outline. So first I will talk a little bit about LioniX International, really short. So who are we and what do we do? Then the platform that we base everything on is called the Triplex platform. It's a Silicon Nitride based chip platform that we fabricate. Then something that we got really big in and which we use to get extra value from the chips that we produce is the packaging. So a little bit of examples. Why this is important and why you should always think about this. Then a little bit of applications in the infrared domain, visible domain, and the near infrared 850. For all these three domains, we have an MPW run. And at the end, I will wrap up and then we can start with the questions. So LioniX International is a leading global provider of customized microsystem solutions with the particular degree of integrated photonics based, and we generally manifest ourselves in scalable production volumes. Why do we do this? Because we think that photonics has a key role to play in disrupting technology to solve major societal issues. So, and that's why we think integrated photonics is the key enabler. That's why a PIC is more than just a chip. A little bit of examples from where we come from. You can see sometimes Xio or Satrax. These are some examples of chips that we make. This is with VCSELs integrated. This is laser beam combiner. And we have our own clean room, or we share it with the university, but we use it a lot. From this chip, we start to make modules. And this is the process we call vertical integration. So we do everything from mask design up to module design. So that means that we're involved in all the steps of the process. So we have knowledge on all these parts, which means that you can make more complex systems, but also better systems. So it's not just delivering a chip. Yeah, we can do that as well, but it's not just delivering a chip and say, yeah, now it's your problem. No, we think about what are you going to do with it in the end? So our Triplex-based photonic ICs are based on the Triplex platform, which usually is a double stripe structure, but we can adjust it to all kinds of structures by adjusting the geometry. You can get access to Triplex really easily with the MPW runs. You can do that through Europractice, or you can just contact me directly. What we also offer, I will get back to this, is characterization packaging. So when you design your MPW chips, you can also decide to have it packaged for a little bit of extra cost, which greatly reduces your headache further on, usually. That's from our experience, we see that it has a lot of added value. So like I already said in the start, we have three platforms. Infrared, which is great for like telecom applications, true time delays, even quantum. Narrow line with laser is one of our most famous ones. Visible light for multi-color lasers, so combining multiple colors or making fringers for structured light, all those kind of things. And near infrared, usually used in combination with optofluidics to create very sensitive sensors. Yeah, a little bit about our triplex waveguide concepts. It's a layered waveguide. So we have, that means that we have a lot of freedom to play around with the thicknesses of the layers and create different applications and different properties. So we have these different kind of layers to make sure that yeah, it is a balanced platform in sense of stress. We have low refractive index and high infractive index, so we can choose how much confinement we have. Single mode, multi-mode, we can do everything. Operating range from 405 to 2300 nanometers. And the most important part is that it's very low loss. This is one of our biggest advantages. One of the disadvantages is that we cannot do active components, we cannot do modulators, we cannot do detectors, we cannot do the gain sections. But as I will show you in the future, we solve this problem by our hybrid integration approach, so that we can get the best of all platforms, which then makes really powerful modules. So these are some of the geometries that we have. Unfortunately, on the MPW, we only have one you can choose from. You cannot adjust the geometry, you can only adjust the width. But we can all make different kinds of structures if you really want. You can adjust polarization properties. You can design by geometry. This is one of the most important parts. It is silicon glass compatible, so even CMOS compatible it is. And one of our most important features is spot size converters, which converts the mode of our high confinement modes. It can convert it to almost everything. So I will get back to that in the next slide. Here's a nice picture of a visible light AWG, which splits light up in different colors, and it's of course visible. You can see it, and we can also do this for infrared, but this gives a really nice picture. A little bit about the tapering, the spot size converters. We can make mode profiles from 1 micron to 10 micron pitch with a different pitch, also with angles, no problem. So this is one of the important parts that we can use in our integration approach. So we have low loss coupling to basically any platform there is. So that means that, whatever you want, you can put it at the end, as long as you match the modes nicely. And you don't get that much extra loss. So that means that we can also use the benefit of all the other platforms like indium phosphide, which has very powerful modulators and detectors, for example. This is a little bit about the history of our chips, that we do get really low losses. The 0.1 dB per centimeter that you always see in papers, that's for our dedicated runs. So these are quite common. This is also a typical result for the asymmetric double stripe. You can go to extremely low losses, so like 0.1 dB per meter, but that's for the single stripe, which the trade-off is then bending radius, for example. Yeah, so how do I get access to this technology? We do offer MPW runs for the three platforms that I mentioned, so 850 nanometer, near infrared and infrared telecom 1550, and visible. Schedules are also on our site, but here they are for the upcoming runs. The most common one is the infrared 1550 one. So, and usually that's designed with Synopsys software. We have a special deal with them that you can, I think Europractice also has a deal with them, and that you can get a PDK, so you just design by building blocks, and then you send the design to us, we incorporate it on the mask, and at the end you get your chips, or you let them be packaged. I will get back to that. So yeah, of course, fix the tape out deadline. If you miss it, go to the next one. So for the MPW, we have an ADS waveguide. This is the infrared one that I'm now showing. For this, we spec a little bit of higher loss because of the processing that we do. 0.5 dB per centimeter. Usually it is a little bit lower. So, but this is like the maximum value. Yeah, the group index is 1.77 for alpha TE. So a little bit about the building blocks. Just a small subsection of what we have. We have tapers, bends, straights. We have for actuation, so switching of tuning phase. We have at the moment on the MPW run, we have chromium heaters. And we can also offer you directional couplers and wide junctions as private building blocks, so you put them in and we fill them in with the according designs. And with this, you can also make all the components that you would need for, like for example, for optical beamforming network, ring resonators, Martinez, we also have components for that. So for example, you see a ring resonator made with a Mach cylinder in there. So a tunable ring, tunable coupling to the ring. So you can, I will get back, I'll have some examples of that, how you can use that for telecom applications. So you can see that this is also an MPW chip that was made in the past. You can see that this also allows a high density integration. So you can see that, yeah, there's a lot of actuators here and a lot of functionality, which is the power of the Triplex platform. You can put a lot of functionality in there while still having relatively low losses. So this is a very important part for if you need long lengths of path or all the complex functionality. We also work together a little bit with Bright Photonics to make, for example, AWGs, as you see here. So if you, for example, want an AWG, you can ask them, I want an AWG with this spacing and this many channels, and then they make a private building block. We incorporate it on the mask, and then you have a nice AWG. As you see here, these are fabricated AWGs, and they are very well spec'd. So. Yeah, so something that we do along the lines, which is not available yet on the MPW runs, but for the microwave photonics, you can see that, like the example I showed, that you have a lot of actuators. So normally we do these actuators with heaters, but to reduce power, we are also busy with piezo actuators, stress-based. We're already very far with that. They're not yet available in the MPW, but I think they will be in the near future. So that means that you can do the same amount of actuation with a fraction of the power. So where a normal heater would take a quarter watt, this one would take a microwatt because it's only purely capacitive. Here are the specifications. It's 3 microwatts. So this is something that we are working on the way. Something that is really important, we have seen over the last 20 years almost, that is that packaging is a very crucial part of any photonic IC. Because in the past, some people, they have a chip and then they think, all right, it's done, but you need to interface it somehow. So you can do that, of course, on an alignment stage, or you can probe chips, and it does work, but if most of you have experience with alignment stages and probe stations, that this is not a really nice way to do it, because yeah, it's not fixed, and it depends a little bit on the skill of the operator. So what do we offer for MPW runs? If you adhere to the rules that we set, we can package this chip for you. It will involve a little bit of extra cost, but this will save you a lot of headache, and I think that's already worth it. So what we do is we polish the chip, we attach a fiber array, we put it on a sub mount so that you have a nice thermal body. We wire bond it, put PCBs next to it so that you can interface with your electrical circuitry. And what we also do is we can also hybrid integrate a laser on this platform. I will have an example of that in a minute. Yeah, so this is standard. So as long as you adhere to the rules, we can package it. We don't care what you have on the chip, but as long as you follow the rules, fine, you can package it. And this means that we can do this at a lower cost. So we have everything in stock, and you can just order assembly, and you get something which looks like this. So sometimes we also use it ourselves because it's very easy. You can see here a visible light application where a Fringer is made. So the visible light is split up into different branches, and with phase tuning, a different pattern is coupled out using mirrors. But this chip was also perfect for packaging on a CPS mount. So that's a really nice example. It's even integratable in the electronics, as you see here. Yeah, so the MPW runs are 3 times a year. Visible and 850 are a little bit less often. So keep a very good track of when they are. For the design, we have a PDK available, which is free as long as you have the correct software. And yeah, the standard guidelines are also included in this and in the design manual. So if you plan on joining, then please read carefully the design manual. Okay, so then a little bit of examples of what we did with Triplex. So I already showed the visible light applications, right? So for example, you see here a beam shaper, which we made for DNA sequencing. Integrated microwave photonic platforms for beamforming, 5G, beamforming, SATCOM, all those kind of things. You see one of the first ones here. You can see the modulators connected here, the detectors integrated, all indium phosphide, and a laser coupled in here. So I have a newer example in a minute. But yeah, this is where we come from, and this is what we do. So this yeah, this shows the power of integration, and you can get a really complex compact module with a lot of functionality. One of our very important parts is the tunable lasers that we make, hybrid cavity lasers. Also compact light engines for augmented reality, virtual reality. You see that these days there's a lot of ask for virtual reality, augmented reality, and that means that you need to have really compact lasers that fit into glasses, and that you can project light into your retina. Also medical stuff like OCT we do for detecting skin cancer. Usually we do that with the 850 nanometer, and biosensors. At the moment, we are also developing a chip that is able to detect COVID-19 antibodies. It's all in this platform. So it's together with Surfix we made that. That's a very nice application. So I will first show some more infrared applications. Beamforming. This is also very important in telecommunication these days, because bandwidths go up. You need to get a lot of data across RF path, and these days the RF processing is also very good, but still limited in bandwidth, and we can go to a very wider bands with also the other benefit that if you choose, you can also end up in a fiber, which then plugs into the telecommunication network. Yeah, there's an antenna. So this is something which we use the ring resonators for, to create delays. For beamforming, you need delays, true time delays, which you cannot do easily in RF. So what we do is we take the RF signal, we put it we modulate it on a laser, so we can get a really large bandwidth. We go through a couple of ring resonators and we can create a phase delay response as we want. So because they are continuously tunable, we can delay a certain part of the signal so that you can correct for antenna angles and all those kind of things. So this is a very nice application of what you can do with the infrared functionality. You can also switch and split light. So this is, you can have a lot of freedom there. And this is a little bit how it works. With again with a tunable laser. I have a couple of slides after this to explain it. We can split it, do it to send it to modulators, filter it, and then do the beamforming. And we can either choose to go to fibers or to detectors. And this is I like this picture a lot because it shows the amount of integration that we did here. So what you see here is the tunable laser here. So we can set it from any wavelength in the C-band. This carrier is then sent to this chip with 10 modulators. In this case, we only use 4. We can split the light up and modulate different antenna signals that are put in here. We can modulate different signals on these carriers, send them through the beamformer, and then detect them with photodetectors here. The small part is photodetector, so that you have a truly RF in, RF out system. So the active components I said we do with indium phosphide, and yeah, the processing we do with Triplex. So that you can see that it's RF in, RF out. So in a sense, you can also remove the fiber. And this also shows that the power comes from assembly. So not just the chip, but also the assembly. So creating a whole module. These are other examples of OBFMs. I will go through them quickly. Yeah, transmit and receive. This one is all RF, RF in, RF out. This one is RF in, fiber out. These were the first ones actually that we made. So this is the first fully integrated ones. But in the meantime, we've already been progressing with this, and we already made even 22-1 beamformers, really big ones. Yeah, you can see some delay curves measured in RF. So on the frequency band of interest, the Ka band, you can see that we can make any delay possible that is used for delaying the electronic signal. But also we can also do dispersion compensation by setting the rings in a slope here, you can see. And this is all over a bandwidth of 3.5 gigahertz, which shows that this is a really wide band application. So a little bit about the tunable laser source, because that's also one that is available on the MPW. This is done by hybridly integrating an indium phosphide gain section with Triplex. Triplex has ring resonators to filter the laser output, and so this way you can make a really low line width, high output power gain laser. And this is what you then can use on a chip to use your functionality. Yeah, this is a little bit, I'm not sure how I'm doing with time, but maybe I'll go through it a little bit quickly. So this is a little bit how it works. It is you have 2 rings, which filters a broadband laser source. It couples it back to the gain section, which amplifies then again, and you have a constant feedback loop like this. And then with the output, you can couple the outputs so that you have a nice laser line, which is tunable over a very large bandwidth, but also has a very nice output power. So this is very usable in the telecommunication industry. Here are a little bit of the specifications. Yeah, they're still getting better. Yeah, single mode, high side mode suppression. And yeah, for single lasers, usually they are between 20 to 40 milliwatts. But we also have already published some of the results that already go towards 120 milliwatts. So, and that's then fiber out. So that's then on chip, it's even more. Yeah, here are a little bit of pictures over the wavelength range. Yeah. So the best laser that we've measured was 290 hertz line width with 30 milliwatts power. So, and then 80 nanometers tunability. And this is something that shows the power of the hybrid integration, because yeah, so that this filtering is done on triplex, and the power is done by gain, by the gain on indium phosphide. But it's also here are some pictures of it. So this is our standalone laser source that we sell, which uses the same concept, but it's also integratable on the MPW platform. So that's also what we offer. You can see here that it's this is one of the templates that you can do, that you can ask for when having a MPW run. You can design here all your functionality, and here you have a laser, which is a private building block. We will put it on the mask, and we can then assemble a gain section here, get a laser, so it's electrically connected here, and then you can do whatever you want on the application-specific design area, and yeah, get great results hopefully with your photonic IC. So we've already been doing this since MPW 15, so that's already 5 MPWs. We use this. We can use this. In the future, we're probably going to also integrate more components, but that's still under development. So another application that I want to shed some light on, because most of it is now what I did was the infrared, the 1550 infrared part. The visible part, because that's a very important part in this for MPWs as well, and for different applications. So in this, in an example, for example, is multi-wavelength beam combining, what you can do. I can show that here. You can make AWGs, putting on the visible triplex chip. This is all triplex. We also have ways to assemble this so that you can get low loss coupling and no burning in effects in these chips. And with these visible light chips, you can do all different kinds of things like spectroscopy and microscopy and multi-beam combining, structured light engines. I can show you a little bit about one of our first devices that combined lasers from different colors to create a wideband laser source with stabilized power control, so you can decide how much power of each laser comes into one fiber. So at the end you have one fiber which has then all the wavelengths in there that you put in, and you can control the power of it so that you have a very stable loop, and you can have any color you want. You can also switch colors. And this is an application that those are very important for microscopy. And like I said, these days VR and AR is also very important. So we've come up with a structured light engine, not a structured light engine, an integrated light engine. So to make it as small as possible, so that you can fit it into glasses, for example. So here you see what some companies think the VR looks like, and this is something that other companies think it looks like. So in both cases, you need very compact light engines to make sure that you don't have a huge apparatus on your head. So in this sense, then you have to use photonic integration. Otherwise, yeah, you won't make it with this. So that's also something that we're busy with. And the other part that is has a lot of applications is the biosensing platform. This is the third MPW run that we also do. This is the 850 nanometer one, the near infrared one. Yeah, this is usually in combination with microfluidics, so to sense proteins, viruses, all those kind of things. Here you see an example of the very sensitive measurements using this 850 nanometer platform with VCSELs flip chips on it. We can sense really low concentrations of chemicals, or in this case, I think it's a medicine, neutrofidin is a medicine, I think. So you can, yeah. So this is an application that is very important in medicine these days. So this is very powerful to do that, and traditionally you don't get this kind of accuracy. Also, something that is important is the OCT system, which we're also busy with making, also on an 850 nanometer platform. This is, you can see that what you do is you send out broadband light calls and you receive it back. And with this, with interferometry, you can then determine the structure of the light of the device in the test underneath, or the person under test in this case. And you can look into the skin, for example, to see if there is some anomaly there. Normally, traditionally, these devices are really big, so you need a card for that. But for us, what we are striving to make here is a device that you can use in your hand, like a pen, and you can just scan over the skin. For that, you need photonic integration to make it as small as possible. We've already had some really good results with that with the first iteration, and yeah, now we're busy developing it further. And this is something that you can use in medicine, but also for other things like I don't know, inspecting welds or something, right? Or electronics. So it's very widely applicable, and this is this is what you can do with this kind of photonics. Yeah, so this is a little bit of a reminder of what you can expect from the MPW runs. So we have 3 on offer. Infrared 1550, used for beamforming networks. MPW for visible, so for laser beam combining and structured light, for example. And 850 for biosensing. Those are the applications that you can think of. We have a PDK available for these MPWs. Like I said, we have a special offer with Synopsys so that you can try the software and run our PDK. Recently, we also are involved with Nazca Design, that they have also a PDK available in Nazca Design, so you can choose between the 2 programs. Yeah, there's of course a fixed tape-out deadline for the design submission, so really think ahead which one you want to pick and then start designing towards it. Yeah, and if you want more, of course, you can also ask for a dedicated run. So a little bit to summarize. Triplex, why triplex? Low losses, optimized interfaces to facilitate packaging, very broad wavelength, so you've seen applications from visible to 850 to 1550, so you can basically use every wavelength you want. And what we are very good at is the hybrid integration with another semiconductor, so in this case indium phosphide, but we can also do other types. Usually we use indium phosphide, but any type is good. Yeah, applications, microwave photonics, biosensing, AR, VR, even quantum computing, COVID detection, everything, what you can think of. And then this is the overview slide. So write down the dates. Now they're also on our site. So.
Yeah.
And now I'm wondering if there are any questions.